The last research infrastructure to be highlighted today is the Fugaku Supercomputer. The importance of powerful high-performance computing is more than ever emphasized, and Fugaku is the great success of our efforts in this field, currently holding several number ones in various performance rankings. Dr. Satoshi Matsuoka, Director of RIKEN Center for Computational Science, will tell us more. Dr. Matsuoka, please.
Oh, okay. One moment. Okay, thank you very much. And it's my pleasure and honor to be able to present at this symposium. We are RIKEN R-CCS is on one hand, one of the 13 research centers and infrastructure centers hosted by RIKEN, but also we are the National Center for High Performance Computing. And the outcome of our research, we do multitudes of research. We publish aggressively in journals and international conferences and so forth, and we collaborate a lot in various forms of research in high performance computing, would also apply the result of our research into constructing the national flagship supercomputer, which in the current form is Fugaku, which I will introduce you today. Next slide, please. Okay, so Fugaku was so named. It's an alternative name for Mount Fuji, because we believe that the mountain, of course, the mountain symbolizes Japan, but also symbolizes our idealism for supercomputing. Now, in the past, Japanese supercomputers were, they had good performance, state-of-the-art technology, but were catering only narrow sets of users. So those users wanted high performance, which naturally were provided, but they were in the modern days of IT. They were very sort of isolated. So Fugaku was designed, constructed, and being operated to change all that, to not only have the highest performance, but also a very broad base of applicability, very large capacity, broad sets of application areas, not just classic HPC ones, but modern days pertaining to AI and big data and so forth. And just to broaden the user base to not just academia, but also the industry, cloud startups, and all of these for the objective of basically improving society through the Society 5.0 Japanese initiative. Next slide, please. Of course, simultaneous satisfaction of performance and applicability is easy enough. It's like trying to build a very comfortable saloon. If it were an automobile, it's try to build the most comfortable saloon that everybody can drive, but can go as fast as a Formula One car. So that's it's very, very difficult. But of course, we met that challenge, and we were able to basically overcome the challenge. It was sort of a moonshot level challenge that we set very high standards, very high objectives. And for that, we really had to build the machine from ground up, not just to buy chips from like the US vendors. But of course, there are a lot of international partners that participated in the project. But the chip, the processor we built, A2FX along with Fujitsu, which is also being held in my hand. Oops. Oh, no. Yeah, right here. Is a new processor. So although it has some European flavor to it, because it's an ARM processor in that it runs the same software as your smartphone, or like the Mac or MacBook, or any of the ARM-based commodity platforms. But of course, internals is completely our own. We designed the microarchitecture, so-called microarchitecture from scratch. None of the ARM IP was used for that. So, and in fact, we because of the various parameters and constraints the objective was to build something that would greatly exceed the capability of the highest performing server CPUs, general purpose CPUs that are built by companies like Intel and so forth, by like factor 2 to 3, or be 2 to 3 times more power efficient. And so Intel is kind of like Intel is very capable, of course. So it's very, very difficult to build something that's a few times better than they are. But we achieved that through extensive collaboration of RIKEN, Fujitsu, and all the partners on the computer science side, but also from the computational science of computing, and that in fact the entire Japanese HPC community gathered together, and the government funded essentially risk money, because Fujitsu itself could not have built this machine. But this risk money, as well as all the smarts, were gathered as a national project, and thus we have the chip and the machine, which uses 160,000 G chips. Now, Fugaku, how powerful Fugaku is? Well, compared to our smartphone that runs the same program it runs the same program as Fugaku, or vice versa. Fugaku is equivalent to about 20 million smartphones, which is about the same number of smartphones sold in Japan over the course of the year. So the flip side of this is that if you have 2 or 3 Fugakus, that would account for the entire compute capabilities being produced and sold in Japan. So that means Fugaku is a major fraction of the Japanese computing capability, not just for HPC, but for everything, like clouds and servers and laptops, smartphones, etc. That's the magnitude of computing that we have assembled in this single machine. Before going on, we were asked to do a virtual tour of Fugaku, so we have to have a video, so we'll show that. Unfortunately, the narration I had done was in Japanese, but it was dubbed. So you will not hear my voice, but a dubbed voice, and there are a few mistakes here and there, but hopefully you'll enjoy it. So can you please play the video?
In this virtual tour, you'll get an overview of the supercomputer Fugaku. First of all, the name is Fugaku, another name for Japan's biggest mountain, Fuji. This was chosen to represent its elevated performance and also its usefulness across a broad base of different tasks. This is where the name comes from. But its actual physical appearance, as you can see, is also that of a very big supercomputer. It's about 50 meters wide and around 60 meters deep. That's a footprint of around 3,000 square meters. So it's also the world's largest supercomputer in terms of the floor space it occupies. Of course, each of these racks is connected together. And the decorative panels on the first row of racks have the Fugaku logo and this blue background. And if you look carefully, you'll see a faint image of Mount Fuji spread out across these panels. That represents how all these components together comprise the Fugaku machine as a whole. Fugaku, like other modern supercomputers, uses a very large number of CPUs, connected by a high-speed network to function as one large machine. We'll get a closer look at what's inside each rack in a moment. But the heart of each rack is a newly designed CPU called the A64FX. It uses the same ARM architecture as chips in many smartphones nowadays, but dozens of times faster. There are 384 of those CPUs in each rack, and 432 racks, for a total of about 160,000 CPUs, combined by a high-speed network into a single machine. That's Fugaku. It's the huge number of CPUs that makes it such a giant. Next, we'll look at the main component of Fugaku, the CPU itself, or what we call a node. All supercomputers, all computers, and even cell phones like this one have a central processing unit, commonly called a CPU. In Fugaku's case, the CPU is this A64FX model, which was newly designed for this project. This is the actual silicon-based CPU, and these CPUs are installed in the racks in this package configuration. You can see it's quite a bit larger than just the CPU itself, and the reason for that is one of Fugaku's performance advantages. You can't see it, but along with the CPU, this package design also incorporates cutting-edge, extremely fast memory chips. In a typical computer, those memory chips are separate. As anyone who's ever built their own computer knows, you buy the CPU and memory separately and connect them to the motherboard in different places. Or, even if you've just added RAM memory to a laptop computer, you know that memory chips go into separate slots. But here, the memory and CPU are combined, making memory access much faster. It's the first general-purpose CPU package with integrated memory. And these CPU packages are loaded onto a board called a CPU memory unit. At first glance, it might look like a normal computer board, but there are three major differences. The first difference is pretty obvious. These copper plates and tubing. We need it because this machine uses water to reduce the heat. Most computers and cell phones use air to cool down. Even large data centers use air cooling. So, if you visit a data center, the noise from the built-in fans is often so loud that you can't have a conversation. The fact that you can hear my voice right now, standing beside a supercomputer, is because it uses water for cooling. The water cooling system allows us to place the components closer together, which improves the performance in a number of different ways. But it's not easy to do, so this was a major achievement for us. The second difference is these connectors, which you might not recognize. These connectors provide another performance advantage of the Fugaku design: the networking. The network that unites these CPUs runs effectively at around 400 gigabits per second, which is roughly the same data transfer rate as an entire data center. A home computer would typically have a data rate of roughly 1 gigabit, so this is 400 times faster. And each of the 160,000 CPUs communicate with one another at that speed. This connector is for the fiber optic network. I'll show you in a moment. Fugaku uses around 100,000 fiber optic cables. And the third major difference is that the memory doesn't reside on the main board. On a regular computer, there would be memory slots here. But, as I explained before, the memory is integrated into the same chip on the CPU package. Each board holds 2 CPU chips, and each server rack cabinet contains 192 boards, for a total of 384 CPUs per cabinet. The boards are inserted here and connected with optical fiber cables. These cables enable the super-fast 400 gigabit data rate. There are 100,000 of these cables for a total length of around 900 kilometers. So it's #1 in the world for the amount and length of optical cables, as well as for network speed. It has the same performance of data centers all over the world. There are 432 racks, with 160,000 nodes that make up Fugaku. Right now, it's already running a wide variety of applications in virtual spaces. So even as we speak, the ingenuity of our research and development is serving people around the world. Thank you for taking the Fugaku tour.
Okay, thank you very much. And just to correct a few mistakes in translation, it was correct in the original Japanese. It's not 900 kilometers, it's over 2,000 kilometers. So actually it's much long. Fiber optics is much longer. And also the data rate, the entire data rate in the machine is more than 10 times that of all the data centers in the world combined, including those of Amazon's and so forth, Google's and so forth. So, there are a few mistakes in translation, but so we apologize for that. Now, so Fugaku, basically, as we explained, we were able to either develop or deploy the leading edge technologies that are not seen in typical data centers or typical CPUs and so forth. And it's not just the processor itself, but also the important part is the network and the total system architecture, including the software. So it's the first chip, it's the first machine to have a general purpose network built into the chip, and also the switch into the chip. So for people who are accustomed to looking at these machines, they may have wondered where's the switch fabric? Well, there are no switches. Well, there are switches because the switch is on every chip. So there are 160,000 switches, network switches in Fugaku, which allows us to scale and also provide the capacity that's required for such an immense supercomputer. Next slide, please. So the performance of, next slide, please. Yes, so the performance of Fugaku, typically one would say, on the newspaper, you may read, like Japan, China, US, Europe, all the countries claiming #1 spot on supercomputing ranks, but usually that's referred to as, they refer to this top 500, which is becoming more of an outdated ranking, actually. But it's important that for Fugaku to have achieved #1, or at least perform very well across many rankings, which represent different facets of applications. Because, as I said, Fugaku is supposed to cater to very broad sets of applications, and just accelerating on one application, would have been a failure. So we're very glad that across many application spaces like top 500, HPCG, or AI, or big data, and simulation and so forth, we were able to achieve several times faster performance than the #2 machines of the world. Next slide, please. But of course, Fugaku was never built to excel in the benchmarks. That was not the objective. The objective was to excel in application areas, especially in areas that are of high concern to society, those SDG goals, what we call Society 5.0, and of course, we should not forget basic sciences. So Fugaku was designed to cater to various areas like health, medicine, environmental disaster, energy, material manufacturing. In fact, the goal was to achieve 2 orders of magnitude acceleration over its predecessor, the K computer. And this was over a span of about 10 years. So acceleration of nearly 2 orders of magnitude, of course, a very daunting goal. As Google can tell you, they said in 10 years they only increased performance by a factor of 5. So that's the average rate of IT. But we said oh no, we're going to go more than 2 orders of magnitude. So we achieved that. The average across these applications, selected applications from each area, is average about 70. Some are over 100, some are, maybe 20, 30 times, but on the average, they're about nearly 70 times faster. Next slide, please. So I don't have time to go into various results. I'll just highlight one application area, which is the COVID-19. So early on, when Fugaku was being deployed for the first time, was still, the racks were coming into our data center. It was, and they were being brought up, but the COVID struck. And it became quickly apparent that we needed to utilize Fugaku as it was being brought up little by little to basically try to solve the COVID-19, try to help solve the COVID-19 problem. But there are many facets of a pandemic, all the way from the molecular, in fact, quantum level, quantum mechanics level investigation. For example, when you have new strains, why are the bondings stronger? What's the mechanism that makes the strains have a stronger bonding? And is it the van der Waals, or is it the electrical charge, how they interact and so forth, according to the molecular structure, to things like drug discovery, but even to larger societal or epidemiological type of investigation, especially things like aerosol, how infections are spread, and people and even epidemiologists weren't sure how this was the exact mechanism, and also how it would impact the society. For example, what would be the economic impact of lockdown? So any sort of policies should follow the scientific disciplines instead of just saying we should lock down, because there should be scientific evidence. But the problem was, of course, the evidence was quite lacking. So these projects were launched on Fugaku, and each of these projects use as much, many of these projects, not all of them, but many of these projects use as much computing power as the number 2, number 3 machines in Japan. So over the course of the year. So any of the project would have required a total dedicated compute power of the second tier machines in Japan, and for multiple number of them, because there were multiple numbers of the projects. But only Fugaku was able to cater to the requirements. Next slide, please. So just to show, there's an award called the ACM Gordon Bell Prize, which basically is awards the most prominent application on supercomputers over the course of the year. It's run by ACM, which is Association for Computing Machinery. It's the most one of the most prestigious awards in supercomputing, and every supercomputing center's application teams aspire to win this award. To some sense, some people may attribute it to the Nobel Prize, but we say no, it's not Nobel Prize. It's more like winning the best the best film of the year in the Academy Awards in the movie industry. But nonetheless, it's very prestigious, and you have to have science, performance, and also technology in order to be able to win, to be awarded this. So it's a really testament of the high performance computing capability across not just the machine but the application and software and so forth. Next slide, please. So we were able to win with the COVID, and give you a few slides overview of what the application is. So basically, we had a very advanced simulation program, CFD simulation program that can handle billions of freedom, not unlike industrial, typical industrial applications, but very, very deep, much more advanced future industrial applications like turbine engines, cities, and real car driving dynamics of real cars, and of course internal combustion. And what the research team noticed, that the act of actually the fuel injection in this internal combustion from a physics standpoint is pretty much exactly the same as someone coughing. I don't know if the animation run. Do you think you can run the animation? Exactly the same as the someone would cough or speak or sing with a loud voice, and it would spew the air droplets and aerosol all over. And of course, this phenomenon was known, but the exact nature of how this was not very well known. There were some experiments, but it was very difficult to do the experiments under any sort of societal situation, because that's where. So, for example, questions like are masks going to work, or are like 2 meter? What's the correct amount of social distance, and what are the prevention measures can we have? These were, although there were some guidelines and rough guidelines, the exact nature of what's happening was unknown, and thus the guidelines were pretty, I would say, naive, very, I would say, fuzzy at best. Even if we remember, WHO initially said masks were not very effective against COVID, which of course was who said that's ridiculous, but that was the initial statement. Next slide, please. So, we were able to team up with many industrial partners, academic partners, and also the government agencies to create many digital twins of societal simulations, like trains and buses, theaters, airplanes, karaoke boxes, because a lot of infections were clusters were occurring in karaoke, and so forth. And we were able to do exact simulations of what's going on, and also with some advanced work with immunologists, calculate the risk of transmission and what we can do to mitigate it. Next slide, please. These are just samples of some of the societal situations we have created, from office space to classrooms, restaurants, masks, face shields, taxis, theaters again. And also, and we were able to continue on throughout the course of the year, and still do continue the simulation with, especially with the Omicron, to assess the nature of how the risk of contagion with respect to the contingency measures we are able to put forth. Next slide, please. So, in fact, we do very detailed risk assessment. We create these very detailed digital twins of, let's say, this is a restaurant, and with all the not just the shape and form, but all with the air filters, air conditioners, and all the works, and do the exact airflow simulation with these microparticles. Next slide, please. And then we are able to, with the epidemiological observations, we can assess the exact risk. This is sort of like a map of infection risks, and determine exactly what's the expected value of the number of infectants, assuming there's one unknown infectant in the room. And then we can say, well, by putting these shields and so forth, or putting the tables farther apart and so forth, what would be how much can we reduce the risk? Or when you have a stronger variant, how much the risk would actually increase? Again, in very quantitative fashion. Instead of saying, this is high risk and low risk, we can come up with a fairly precise assessment of the risks involved and how we can mitigate them. Again, and this whole scenario of various societal simulations took more than 22 million node hours, which is more than any supercomputer in the world in Japan can provide over the course of the year. Next, any other computer besides Fugaku. Next slide, please. And this was not only this was widely communicated to the public, and of course that allowed the Japanese populace to be really aware of the importance of wearing masks, and also being very cognizant of the infectious risks. And also, this was adopted by the government, by the Japanese government, of course, the industry, but also the Japanese government, and was made part of the mitigation standards and policies for COVID-19 to reduce the risk of COVID-19 transmission. And in a very continuous fashion, by the way. Next slide, please. Okay, so this is my final slide. So the Fugaku is sort of an exascale machine, as the title says. It's a state-of-the-art technology, some of which we developed, some were we adopted, as exascale performance, but not only just compute, but also in terms of the bandwidth, which is more important. It's been a #1 machine in the world in all conceivable performance metrics for the past 2 years, but also we have won the COVID-19 Gordon Bell Award. Fugaku is open. Fugaku provides about 1.3 billion node hours, or about 60 billion core hours, which is about 40 times the price allocations. But this is open to researchers all over the world, not just Japanese researchers. To the industry, the pure industrial research, industrial usage is restricted to companies that do R&D in Japan. But for academic research, it's purely open. There are no restrictions that you have to be a Japanese researcher. So you can apply. In fact, anybody can apply from Europe. And in fact, we have many collaborations with our very friendly partners, whom we have collaborated over a number of years. The major world-class European centers like CEA, ULIC, Supercomputing Center, Barcelona, and of course, Kimo will present CSC, which will be the next European leadership machine. And we're very looking forward to the collaboration, Swiss CSCS, ECMWF, etc. And of course, globally, we collaborate very closely with the DOE US DOE centers, but also Asian centers, especially headed by like Singapore, but more recently, countries like Thailand, which is also bringing up a world-class supercomputer. So we are quite collaborating. Our user base is collaborating. We had a workshop with the European Commission with respect to materials and also with biomolecular research on supercomputers. And hopefully we can even increase this collaboration because we are getting ready for the next one, which will be even harder. Thank you very much.
Thank you very much for this rich presentation. Some of you might have remembered that the K computer, previous computer, was mentioned in the video we played earlier today, which was made about a year ago. And within 1 year, we just saw that the new machine Fugaku has been already in use to this extent. So this is the pace of research and development.